Hello everyone. Today we'll start the final part of our course, which is reaction dynamics. Now we'll discuss first how one can actually model the reactions and get an expression for the rate constant so that it resembles the Arrhenius rate equation, because if you remember that Arrhenius found an exponential dependence on temperature, 1 over temperature, and then he found that it can be connected to some energy which is some kind of a barrier a reaction the reactants face in order to form a product. It's an energy barrier, and we discussed it in the last lecture, and we'll see today how one can formulate and or get an expression for the rate constant. And to begin with, we'll just discuss the reaction dynamics in the gas phase only. Condensed phase reaction dynamics we won't discuss here, because that is beyond the scope of our of this course. And also we'll first discuss, just to you might have studied kinetic theory of gases a little bit in your high school, but we'll again do a quick review so that everyone is on the same page, and then we'll start what is known as Maxwell Boltzmann distribution of molecular velocities, and then we'll use that to calculate the reactive cross section, and from that we will calculate the rate constant. Now after this lecture, you can actually go back and read or have a look at the lecture number 9 part 2. So 9 part 1 we discussed about electrochemistry or equilibrium electrochemistry, where we just discussed the electromotive force and writing it in terms of connecting it with the reaction free energy. And then in the part 2 of lecture 9 or module 9 was actually discussing the transport phenomena. So that's a kinetic phenomena in some sense. You can also you could have also had listened to this to that video after the kinetics part, because that is the only time dependent part which we discussed under thermodynamics, and that part we called as this dynamic electrochemistry, not the equilibrium electrochemistry. So you can go back and again have a look at that particular part, so then it will be very clear. We clumped it together at that time. The reason is it is under both the lectures or both the topics are under electrochemistry. Although the first part was under equilibrium electrochemistry, that is connected to more thermodynamics, and the second part is connected more to kinetics. Now to begin with, about reaction dynamics, so we'll be talking about gas phase reaction dynamics. And again, just to remember, we want to find an expression for the rate constant that looks like the experimentally determined value which Arrhenius got, and particularly we want a physical explanation for this activation energy. And sometimes you can see that I probably wrote KBT in the other day instead of RT, but that just means that you are talking about only one molecule or 1 mole. If it is 1 mole, then you write this. If this activation energy is part 1 molecule, then you write KBT. If it is 1 mole, then you write RT. So that is obvious. Second thing is that this pre-exponential factor which Arrhenius got. So second thing is that this pre-exponential factor which Arrhenius observed experimentally. The question is, what is it? I mean, can you get an expression for this? Does the rate constant depends only temperature, like only through this term, or also this pre-exponential factor is has some time dependence? Those questions we'll answer today and in this lecture. Now to begin with, let us first discuss the kinetic theory of gases. And all of you know what is the kinetic theory. The kinetic theory of gases was developed by many people, and most significantly by Clausius and also by largely by Maxwell and also by Boltzmann. So what we are right now discussing is the pre-Maxwell Boltzmann development, where the physicists were thinking about gas molecules to be composed of all these gas molecules are basically move in a random erratic motion, and that is known as the kinetic theory, and this motion is connected to the absolute temperature of the gas. Now the first thing first, what you can calculate is since the molecules are moving, so if you put them in a container, these molecules will strike the wall and bounce back, do something like that, and this bouncing back or this collision will exert a pressure on the wall. Now if kinetic theory is correct, then you can calculate this pressure, and then which you can measure because pressure is a macroscopic quantity, and then you can actually get an expression of the pressure in terms of, say, molecular velocity, something like that. So that we are going to first derive. Now suppose we have an wall and a molecule is coming in this direction. Now although I'm writing the molecule like this, strictly speaking, in kinetic theory of gas, the molecules were particularly for the ideal gases, the molecules are considered as point mass, so they do not have any dimension, but they have some mass. Say that mass is m, and suppose this is the x-axis, and the velocity component along the x-axis is vx. Now suppose the molecule does a collision, and there is no energy exchange between the molecule and the wall, and so it is a kind of elastic collision. But the momentum change, if we take this as our positive x direction, so the change in momentum is the final momentum, which is mvx. So the initial momentum according to this will be minus vx minus the initial momentum, which was minus mvx, so which is nothing but twice mvx. And all we are going to do is that this to calculate the pressure is nothing but force per unit area, and force is connected to this rate of change of momentum. So that we are going to use just from Newton's law. Now the question is, if you what we're discussing, if this choice of this x-axis, which is in the positive in this case, I could have chosen in the other way. So what we are saying is that it is the overall magnitude change of the momentum. So if we had chosen the other way, it will be just minus twice mvx. But it doesn't matter. We are only concerned with how much magnitude it is changing. What is the total change in momentum? Now consider that this is for only one molecule, and to calculate the pressure, we have to calculate or the force. So we have to calculate some cross-sectional area on the wall. So suppose this area is A, it's an arbitrary area, and we have to ask this question, okay fine, how many molecules are basically striking this wall, and what is the total change in momentum? Now to calculate how many molecules, you need to know the volume. Okay, so what volume we'll choose? So suppose we are asking this question, at some time delta t, how many molecules actually are within this zone? So that will be fixed by, if the time is delta t, if I multiply by the velocity of the molecule, which is vx, so that distance will be covered by any molecule which is lying within this linear distance, because any molecule lying outside here, so that will take a longer time to cover this, to come and hit this wall. So within this distance, we mean that, or within this distance is given by this, whatever molecules are there, they will strike. And so the volume is given by nothing but this area times this distance, which is A times delta t into Vx. And then we have to calculate the number of molecules which is striking. That number of molecules is given by nothing but the density of the molecules times the volume, because density is the number of molecules per unit volume, and multiplied by volume, it's nothing but nothing but this number of molecules which are within this cylindrical volume, within the cylinder, which will strike the wall within this time delta t. So this is the number, and then into delta t, A into delta t into Vx. So the total change in momentum, which is basically force, that will be equal to each molecule's change in momentum is twice mvx, and it will be multiplied by rho a delta t into Vx. Now we are not interested in that will be not the force. Force is basically rate of change of momentum, remember. So to calculate the rate, we have to divide by delta t, of course, because it is within the delta t interval how much momentum was changed. And then if I divide it by the area, I'll get the force per unit area, which is nothing but the pressure. Now in this calculation, we actually assume that all the molecules which are within this cylindrical container or cylindrical volume are actually moving towards left, but molecules have equal probability of moving towards left or right. So we have overcounted the number of molecules, so we should actually calculate when we calculate it, so we have to calculate it by multiplying another half here. So let us just write the half here, Vx into half, and now you can see this 2 and this half cancels, and also I am dividing by area to get pressure. This arbitrary area cancels and this delta t cancels, so these are just arbitrary parameters. So what I'm left with is nothing but m into Vx we have, and then rho. And rho, actually, instead of rho, we could write it as n by v. It will be clear why I'm writing the rho again as n by v. Now, this pressure, if the gas obeys the ideal gas equation, then we know that PV equal to n at T. Now, this n is the number of moles. So better actually denote our old n as capital N, which is the total number of molecules. So we are just multiplying it, just a minute, it will be m, rho was density, and we had m, and let us write this Vx square, and then if we had a rho, and the rho we are writing as n by v. Now we know that PV is equal to n at T, and what is n? N is just number of moles, so which means actually it is definitely n divided by n Avogadro number. So total number of molecules divided by Avogadro number times R times T. Now you can see that this R by n Avogadro is nothing but the Boltzmann constant. So we can also write that it is n into kb into T. Now you can easily now calculate what is P from ideal gas equation. P is nothing but n by V into kb into T. We could have written it as rho and just kept the rho in the above equation. It is just obvious that this n by v terms will cancel. So what we get ultimately is an interesting situation that mvx square is nothing but kbt. Now you see this pressure will be what the way we have written it is this pressure is getting contributed by only x component of the velocity, which is not very correct because the molecules are moving in all possible directions. So what we could write actually at this point is that how this pressure is connected to the velocity. Which velocity? That velocity which is basically the independent of the direction. And also think about it, the way we have written the velocity, we have written on particular velocity every molecule has, but that is also not true. On average, the molecule will have, say, average of the velocity, which we can write it as Vx average. Now the question is how you will connect this average velocity with the just the magnitude of the velocity, which is nothing but the speed, so which is independent of any direction. Now we know that this v square, which is just the length of the modulus length of the velocity vector, is nothing but vx square plus vy square plus vz square. And we also know that vx square should be identical to, or the average value of the vx square should be identical to average value of vy square, or should be identical to average value of vz square, because the gas usually is isotropic in nature, and the top equation also we can average out. So these two conditions give that Vx square is nothing but 1/3 V square average. So we could directly write it here instead of this V square. We're now using that we have to use the average velocity, and so the expression for the pressure will be mass times N by V times Vx square average, which is nothing but 1/3 of V square average. I'm writing the 1/3 at the beginning, N by V into V square average. Now this expression you compare with this expression, because those are two expressions for the pressure, and you can easily get the value of V square average. So you'll get that V square average is nothing but, you can see this N by V will cancel. So we'll have this cavity, we'll have this 3 cavity, because this 3 will be multiplied with the cavity, by mass. Or sometimes we also are interested in calculating the root mean square average, so which is nothing but you take the V square average and then square root it, and that will be square root of 3 kbt by m. So this is an expression of the velocity, or the average, not velocity, it is the average speed, or the square of average speed, which we know, which we call as mean square speed, that is connected to temperature of the gas. So, and that is known as basically, that is the one of the greatest discovery, which laid the foundations of kinetic theory of gases. So we'll be frequently using this relation, and we'll see that how using this relation one can calculate the parameters in the Maxwell Boltzmann distribution. Now we'll start our, so far what we have discussed is that we just discussed the essence of the kinetic theory of gases, and we said that how pressure can be formulated by assuming that the gas molecules are basically composed of a number of, the gas is composed of a number of molecules which are constantly moving around, and they'll strike the wall of the container they're in, and that striking at the wall will cause the momentum change which is related to pressure, and that's a molecular interpretation, you can say, of the pressure. But when I say molecular interpretation, this is actually these molecules are now behaving classically. They are obeying classical mechanics, the Newtonian law. Remember that. There is no quantum mechanics here. But still, there is an idea that the molecules exist. And because this mass you can see is actually mass of a particular gas molecule. Now, and they are striking the wall. And then after they strike the wall, they cause a pressure, but pressure we could have also got from a macroscopic experiment by combining Boyle's law and Church's law, and also the concept of Avogadro, and then we get the ideal gas equation, and we are arguing that if the gas obeys the ideal gas law, then we can get this expression. Now, one crucial point, even if the gas does not obey the ideal gas equation, this expression will still be correct. The reason is we are only, suppose there is a non-ideal gas, but the distribution of the pressure, of course, we have to use the van der Waals gas equation there. The pressure will be slightly different, but we'll argue that the distribution of the speed or in Maxwell Boltzmann distribution will still hold. The reason is this distribution is over only kinetic energy of the gases, and even if there is an interaction present, that interaction comes into the potential energy of the gas. But we are only interested right now how the molecules are moving around. We are not imposing any condition that what is the internal energy, internal or better I should say that what are the energy of the internal degrees of freedom, like for example vibration, rotation, translational, how those degrees of freedom are affected if there is intermolecular potential. Those we are not considering. We are only considering the molecular speed distribution, and that will be the whatever expression we'll get using this ideal gas, using the velocity expression which we derived using the ideal gas expression, will also be correct for real gases. That we'll just argue, but we want to be proving it here because this needs understanding of the that's called actually configuration integral in statistical mechanics. That will not discuss here. Now, to begin with, what Maxwell Boltzmann distribution says, which is basically developed by James Clerk Maxwell, and then Ludwig Boltzmann extended it to find the statistical interpretation of the Maxwell Boltzmann distribution. And so what it says is that there will be, when we have a collection of molecules, so not all molecules are moving at the same speed at a time. So what is happening here, the molecule suppose is moving, say, just take a number, say 1 kilometer per second, and then it collides another molecule which was moving in some other direction with some other speed, and then due to this collision they exchange their kinetic energy, and then maybe the faster molecule becomes slower and the slower molecules become faster. And then what will happen is that their molecules are not only moving around, they are also at different velocities. Every molecule is also constantly changing its velocity. But on statistically, what you can say is that I have many molecules, and there is a distribution of velocity. Suppose this is the value of the velocity, or say speed. I should always say speed, because we're just considering the magnitude of it, so it is independent of its direction. That's exactly what we're going to evaluate. Now, suppose a molecule has a particular velocity in this, which is suppose a very specific velocity, which is suppose this v initial, but after collision it just its velocity is changed to here, but then in the next collision its velocity is changed to here. So the velocity is randomly changing. But what we can always say is that other molecules' velocity are also changing. So if you consider a narrow range of velocity, which is, say, for example, a narrow range of speed, which is v to v plus dv, within this narrow range, the number of molecules which are basically, if I just on this axis, if I just plot the probability of these molecules of having some speed, say v, so that will be kind of constant within this range. Why? Because some molecules are changing, every molecule is changing their speed due to collision. But if you have a large number of molecules, so statistically, you can say that within V and dV, the total number of molecules, or the probability of having the molecules in that narrow velocity range, V to V plus dV, will always be independent of time. Now that means, actually it doesn't mean that all the molecules, if I take a snapshot and if I find that some, say 1000 molecules are having speed in this particular range, but in the next instant I'll also have 1000 molecules, but those 1000 molecules are not the same 1000 molecules, because some molecules due to collision have changed their speed and they have moved out of that velocity range. But statistically, similar number of molecules, same number of molecules also entered in that speed zone due to collision. So on average, this number doesn't change, and we're just going to calculate that average. Now we'll make some assumption to begin with. I mean, there are many ways to derive this Maxwell Boltzmann distribution of molecular speed, but the way we are going to do is slightly, I would say, less rigorous, in the sense that it will mostly, I mean, do it on a conceptual basis, but you can do it on a very rigorous way by calculating the energy levels, so kind of Boltzmann's approach, and then calculating the statistical probability of finding some molecule in some energy state, and then you can solve this equation based on constraint using Lagrange's method. All these things we are skipping, and then you can get an energy distribution, and then you can convert it into velocity distribution. That is one of the standard ways of doing it. But right now what we are doing is we are first doing the velocity or the speed distribution, and then we will derive the energy distribution. It is the other way. So it is basically the kind of Maxwell's way of doing it, although it's not exactly the same way which Maxwell derived. Now the logic behind this is that in this Maxwell Boltzmann distribution, we call it as a Maxwell Boltzmann distribution of molecular speed. But it can also be the atomic speed. Suppose if you have an atomic vapor, then also it follows the Maxwell Boltzmann distribution. So now the assumptions are, think about it, our molecules are moving around, and then the first assumption we are making that the molecule has an equal probability of going into the right or going into the left. Now what we are going to formulate is some kind of probability function which is known as a distribution function, because actually it tells us a particular distribution or probability of the molecular speed, distribution function of V. And suppose I'm just drawing arbitrary, so this is suppose the distribution function, which means this particular velocity is very less probable, however this particular velocity is very, very high probable, something like that. So that function, what is the nature of this function, that we want to calculate. So that function I'm just writing as some f. Now that function, when first we will calculate the velocity, suppose the velocity function, and then we'll go to the speed function. We'll basically make sure that we are calculating the some distribution which is independent of the direction. That will give us the speed distribution. So what right now I'm saying is that the molecule should have equal probability of going into this direction versus this direction. So its speed distribution, or the velocity distribution in either direction should be same. Now if you can think about it, like if it has a biased distribution, meaning in one direction the molecules have a higher probability of going, which means that all the gas molecules will have a net velocity in some particular direction. So that is useful when you are considering flow of molecules. But here we are not considering any flow. Here we are considering the molecules are all content in a kept in a container, and there is no net and there is no biased flow in one particular direction. So this function f of v, then whatever function it is, will be independent of the direction. Right now we are again considering first the velocity distribution. So because we are considering right now telling about right or left, which means it has a directionality, which means it's a velocity distribution. Now we are saying that that has to be identical to minus Vx, which means if I calculate the probability of having a velocity with plus 10 kilometer per second, that will be exactly in x direction, that will be exactly equivalent to the probability of the molecule going into minus x direction with plus 10 kilometer or minus 10 kilometer per second velocity. So that is the meaning of that. So that immediately tells me that f of Vx should be an even function. So you know what is an even function. So for example, if f of x is suppose x square, that's an even function, because if I choose x to be plus 1 or minus 1, the value of f of x is the same. However, if it is x cubed, something like that, it's an odd function. F of x will be minus of f of minus x. This even function said the functional form will be something like f of Vx will be something like f of Vx square, just like we saw. It can be also higher order term, like it can be f of Vx to the power 4. That is also an even function. So it's not only a function of Vx, it's a function of Vx squared. That's why it's an even function, or Vx to the power 4. Or maybe a combination of many other things. But we'll first see what happens with Vx square, and we'll argue that all these things actually are not correct. All these higher order even functions. Now, second thing is very interesting, that when a molecule is moving, it is moving in arbitrary. It always moves in an arbitrary direction. Now that arbitrary direction or the component of the velocities along that arbitrary direction, we resolve that into the laboratory frame and ask this question, that what is the component, x component of the velocity, what is the y component of velocity, what is the z component of velocity. Now when the molecule is moving, these components x, y, z, these are basically independent quantities, because these are as you know that this velocity along x does not depend on the velocity of y. If it does, then it will be very different. So the x component velocity and the y component velocity or z component velocity, they're just independent component of the velocities. So what does it mean is that the distribution function, the entire distribution function, which basically says, okay, fine, what is the probability of a molecule having velocity Vx, Vy, velocity components as Vx, Vy, Vz, that will be just a multiplication of the probabilities along Vx, along Vy, along Vz. Now, what is this, where this is coming from? Suppose you have two coins, and each coin has a head side and a tail side. And suppose we have two coins, and then you toss the coin. Suppose you toss the first coin, you just do some huge number of experiments, and then suppose you do it 1,000 times, you toss it, and there you will see that on a statistical way, you will see more or less that there is a half probability of having an outcome as head, and there is a half probability of having an outcome as tail. Now suppose you bring two coins together. So each one has a head and tail side, two sides, and both of them has one head side and one tail side. Now you toss the two coins simultaneously and ask this question: what is the probability of having head head, head tail, tail head, and tail tail? Now that you will see that those probabilities will be nothing but 1/4, and because there is a half probability of having the first coin in head with a head outcome, and similarly there's a half probability of having the coin in the second coin in to have the head outcome. So the total probability will be 1/4. Now this will happen. This is happening because the outcome of the first coin is totally independent of the outcome of the second coin. So if you because they're not talking to each other, they're just independent measurements. So exactly similar thing we are using here. So since these are probabilistic distribution which are independent of each other, the joint probability of having head and tail together, or joint probability of having molecule with simultaneously with speed x-axis component of velocity as vx, y-axis component as vy, z-axis component as vz, will be just multiplication of the individual probabilities. Now the third thing, which is very interesting, is that if this is correct, that I have a joint probability, and also now we see that this thing these velocity distributions are basically the joint probability. We can explain it more. Let us discuss the third point first. So the third point says that we have ultimately we are going to calculate a 3D distribution, in the sense that the molecule is moving in this direction or this direction. That we are not going to calculate which direction it is moving, because it's isotropic in nature. What we are interested is to find the speed of the molecule in any arbitrary direction. The reason is since there is no preferential direction, you can always argue what is the probability. The probability of having the molecule or having the number of molecules in with a say velocity from say 10 kilometer per second to say 10.1 kilometer per second, because always probability means you have to consider a range, because you're considering a number. Probability is just the total number divided by those number of molecules divided by the total number. So you have to always consider some weight. Now if you ask this question that okay fine, if I have this molecule going in some particular direction, then what is the probability of having the molecule having speed say 10 kilometer per second to 10.1 kilometer per second in this direction? But those two probabilities will be identical, because if it is not identical, then again the molecule will have a net flow in some other direction, which is not true. Which means actually this what we are going to calculate is only this magnitude 10 kilometer to 10.1 kilometer per second, independent of the direction, if we really want to calculate a three-dimensional distribution. So what we are going to calculate is a speed distribution finally, not a velocity distribution. We'll start with a velocity distribution, but we'll end up in a speed distribution. So this 3D distribution depends only on v. V means actually I'm writing v for speed, the magnitude of the velocities. So it's only on the v, and then this is just a logical foundation. And the fourth thing is that whichever way I calculate v, I know that this average value of this v square should be equal to 3 kBt by m. That we have already shown for kinetic theory of gases. So these are the main four main assumptions or axioms that we are going to use, but we gave a logical explanation for each of them, why, and we are applying it. So the first thing is that it has to be an even function, because there is no preferential direction of movement for any velocity component. Second thing is that each velocity component is independent of each other, because they are just probability distribution. So the joint probability will be just the product of individual probabilities. The third point is that what we are going to calculate is independent of direction. So we are only going to calculate the magnitude of that, because if I ask you the magnitude in this direction and magnitude in some other direction, these two will be just equal. So a three-dimensional distribution only depends only on the speed, not the velocities. And the fourth thing will be this average value of this square of the speed should be equal to 3 kBt by m, as we derived from the kinetic theory of gas. So in the next part, we are going to discuss, we are going to use all these 4 assumptions, and we are going to basically, based on these assumptions, it's not assumption, it's a logical reasoning. Based on these 4 reasonings, we are going to derive the Maxwell distribution of molecular speed.